Okay, possibly we start our scientific part of our conference and morning session. And first talk is by Professor Imre Csiszár. It's called Common Randomness in Information Theory.
Thank you. So it's not good to start to be first after such a substantial dinner, but anyhow. So I would like to say just a few words about my contacts with Rudolf Ahlswede. Probably I was the first one after Professor Jacobs who met Rudi. It was in the early 60s. I forgot the exact year, but it was an instructional conference in Durham, England. And then I met him at several meetings, including one in Hungary, Debrecen. And then, more substantially, in 1973, when he was in Columbus, USA, and my young colleague János Körner was visiting him for a year. And at that time, I was also visiting in the US, so we met there. That was the time when multi-user information theory started to develop, and Rudi was one of the key players in that game. Later on, when he returned to Germany, we often met. He often came to Budapest and invited several of my colleagues to Bielefeld. So there was a rather close research contact. Later on, I visited him also several times in Bielefeld, including a whole semester when I lived in his home with my family. So it was really a nice time, and he was able to live with my 3 children together. And well, that was a time which all of us have a good memory of. And scientific contacts continued. We had several joint works, and this time I would like to speak about one of the more recent joint works, which involves common randomness in information theory. So I just turn to the mathematics. So what is common randomness? Common randomness means that 2 or several parties have access to the outcome of the same random experiment. That is a very useful concept in several disciplines. For example, in computer science, the availability of common randomness to different terminals makes it possible to develop distributed algorithms, distributed randomized algorithms. In the theory of random codes, of course, a random code can be used actually for information transmission only in the case when common randomness is available to the sender and receiver. And interestingly, in this context, it's enough if a very small amount of common randomness is available. Ahlswede showed that if, for example, in the case of arbitrary varying channels, if a very small amount of common randomness is available between the sender and receiver, then we can already achieve the so-called random coding capacity. So this gives rise to the celebrated dichotomy theorem of Ahlswede, that the capacity, deterministic code capacity of an arbitrary varying channel either equals to the random coding capacity or is 0. Then identification capacity, about which we heard yesterday, developed by Ahlswede and Duc, is closely connected with the concept of common randomness. And perhaps most importantly, common randomness is very key concept in cryptography, because a secret key is nothing else than a common randomness which is secret from an adversary. So here, systematic information theoretic treatment of this concept was developed by the 2 of us in two papers, 93 and 98, and all results which I will present without attribution are taken from that paper. So here are definitions for all random variables will have finite range, and all logarithm exponents are to the base 2, as usual in information theory. We say that a random variable v is epsilon recoverable from another random variable u if there exists a function f such that the v is equal to f of u with probability at least 1 minus epsilon. And typically the u will represent the knowledge of some party, a person or a terminal or something, and in that case we say that v is epsilon recoverable for party A. Now the epsilon common randomness for two or several parties is such a random variable which is epsilon recoverable for each party. And in most cases it's good if this common randomness is nearly uniformly distributed, then it is called uniform CR or UCR. So if the entropy of K is larger than the log of the cardinality of the size minus epsilon, then it is called a UCR. And in many models, the joint distribution of the underlying random variables is unknown. It can be any member of a family of feasible distributions. And in this case, we speak about epsilon UCR if these random variables represent epsilon UCR under each feasible distribution. Okay, so a key lemma which was presented in this 98th paper of ours is the extractor lemma. So suppose P is any family of probability distributions and a finite set U, and an extractor P for P is a mapping from this set U to 1 to K, such that for any random variable U whose distribution belongs to this family, the distribution of kappa U is nearly uniform, in a sense to be specified. So now the concept of extractor is a very basic concept in computer science, and this kind of extractor is called a deterministic extractor in computer science, and they mostly work with so-called seeded extractors or stochastic extractors, but for all purposes the word extractor will always mean a deterministic extractor like this, so a deterministic function. And the dilemma says the following: so if we have a random variable u with distribution p such that there is an upper bound to the probabilities in this set, then for a randomly selected mapping kappa, this condition is satisfied. So the distribution of kappa u is nearly uniform in a very, very strong sense. So the difference of kappa, probability of kappa u is equal to I minus 1 over k is less than or equal than epsilon over k for every I, with probability at least this much. So maybe it's not easy to see what is going on here. So in typical situations, the d is exponential. So there is some parameter n, a block length parameter, and the d is typically exponential in this block length, and also the k is exponential in this block length. And therefore, if the exponent of d is slightly larger than the exponent of k, then this term is exponential, and this whole business is doubly exponentially small. So that the upshot is that in most practical cases, the probability that this is not true is doubly exponentially small. That is the importance of this lemma. And so in this paper, this lemma was called the coloring lemma. You know that Rudy was liked combinatorics, where coloring is a key concept, but with present terminology, I will call it extractor. Yes. Now, okay. So it means that if P belongs to a set P, then this randomly selected mapping will be an extractor for the family P in a very strong sense, in this very strong sense with probability accepted, with such probability. Okay, now what is in common terminology is we call the minus log PU, the minimum of this minus PU, the mean entropy of the distribution P. And then the lemma says that the random selection yields an extractor with probability close to 1, which extracts robust uniform common randomness in a very strong sense. The amount of this common randomness log k is close to the smallest mean entropy of the distributions in the family. And this is a strong statement, but not very useful in this strong form, because this condition about the mean entropy is a very strong condition, so it can be relaxed a little bit, and this is what will be actually used. Here the extracted common randomness will be a weaker one. The near uniformity will hold only in variation distance, which is still a rather strong concept, but we do not require this strong mean entropy condition. So the corollary says that if this inequality holds for U in a subset of capital U, whose this probability of this subset is close to 1, bigger than 1 minus eta, then a randomly selected mapping still satisfies this. So it is nearly uniform in the sense of variation distance. In the sense of variation distance, the distribution of kappa U is nearly uniform. This distance is less than epsilon plus 2 eta, with again with probability like this. And if we have not a single distribution but a family, then we just multiply here by the size of the family, and we get an extractor for a family. Okay, so let us now discuss the concept of various capacity concept. So the problem is, which is a major problem in this field, we consider various models of generating common randomness which involve increasing block length n, and we want to determine the largest amount of common randomness which is achievable within the model. And this problem is very similar to the standard problem of information theory, the information transmission, which is central to information theory. So a channel capacity for transmission is the largest possible rate of reliable transmission over a given channel. So that is the standard problem. But you already heard yesterday that Rudy was he had great dreams, which often came true. So he argued that this is a very restricted sense to look at transmission capacity. Why not look to other kind of problems? And he argued that there are various other problems which are of equal interest, like the common randomness capacity, the largest rate at which common randomness can be generated within the given model, or related identification capacity and secret key capacity. So he argued that there are various problems which are of equal interest as the transmission problem, and information theory should deal also with such problems. He called this the general theory of information transfer. Okay. So in many scenarios, this is just a remark, that common randomness, of course, can be generated in such a manner that it is generated at some point. So the one party throws a coin many times and generates randomness, and then transmits this randomness over a channel to other parties. That is the trivial way. But in many cases, common randomness capacity is larger than what can be achieved by simple transmission. So there are better ways to generate common randomness in many cases. So here are some models. Simplest model, discrete memoryless channel. There are two parties, Alice and Bob, like standard in the literature. So suppose Alice can transmit messages over the discrete memoryless channel, Bob is the receiver, and then if they do not have other resources, then the only way to generate common randomness is for Alice to generate common randomness, transmit over the channel. Then common randomness capacity is equal to the usual capacity of the channel. Other model, however, that Alice may see also the outputs by complete feedback. And in this case, more common randomness can be generated. It is not the best way to generate the common randomness for Alice to generate it. Rather, Alice simply transmits a sequence of IID random variables such that the output random variables should have maximum entropy. And then the common randomness capacity equals this maximum output entropy, because the output randomness will be the common randomness, because the sender sees the outputs. There are similar models when the discrete memory channel is replaced by an arbitrary varying channel, AVC. By the way, Rudy worked a lot on AVCs. And this means that at each time instant, the transition probability matrix that governs the transmission may be any member of a finite family of matrices, maybe even infinite family, but restrict attention to the case of finite family of matrices, which depend on the unknown state of the channel. And then we need the robust version of the definition of UCR. We want to generate over this arbitrary varying channel a common randomness which is available both for the sender and to the receiver, and whose distribution is nearly uniform no matter what channel probability matrices were in use. It is interesting that the common randomness capacity of an arbitrary varying channel with complete feedback is positive whenever the random coding capacity is positive. And this observation, which we made in this 98 paper, shows that the alternative, the dichotomy theorem, is not needed in the case of arbitrary varying channel with feedback. In this case, the capacity for average error is always equal to the random coding capacity. Because if the random coding capacity is positive, then common randomness between sender and receiver can be generated, and then the Ahlswede's random code reduction lemma works. Now let me say a few words about source models. Here we have a sequence of pairs of random variables. Pairs are IID repetitions of a pair of correlated random variables x and y. Alice sees the x output. This is called a multiple source in the terminology of information theory. Alice sees the first component source, the xn's, and Bob sees the second component source. And in first variant of the model, Alice may send Bob a message M, which consists of NR bits over a noiseless channel. And then if this R, so the rate at which Alice may send messages to Bob, if R is bigger than the conditional entropy of x given I, then she can make x and epsilon recover for Bob, sending a suitable message. This is the so-called Slepian-Wolf theorem, that if the receiver sees the y, then it is not necessary to transmit at full entropy. Conditional entropy suffices for the receiver for the second person, Bob, to reproduce the xn. So in this case, the common randomness capacity will be equal to hx in the case when the message of Alice is required to be a function of xn. This is a common situation that Alice cannot randomize. So what she can do is just to transmit a function of what she sees. And in this case, clearly it is not possible to generate more common randomness than the entropy of x. So in this case, we can achieve hx. If the rate is Okay, what happens if Alice can randomize? So if she can send random bits, then she can send nr1 bits with r1 nearly equal to this conditional entropy, which are equal to a function of this xn. And additionally, she sends n times r minus r1 random bits, and then she can achieve hx plus r minus this. So this is equal to this. This will be the common randomness capacity. Of course, we have to show that it is not possible to achieve something better, but it's not hard. Okay. Now a second model, okay, the same model if the R, the permissible rate of transmission from Alice to Bob is smaller than the conditional entropy, or alternate model that when Bob receives the message from Alice, he can send a return message. Or maybe there can be communication in several rounds. Then it is more difficult to determine the CR capacity. First contribution to this case was by Ahlswede Balakirski in this paper. Now, if several rounds of communication is permitted with a bound on total rate, then the common randomness capacity is still unknown. Now, here is a theorem about the common randomness capacity for source model when the permissible rate of transmission by Alice is less than the conditional entropy. Then the expression is given by a maximum like this. These are mutual informations. U is an auxiliary random variable, so we have to consider auxiliary random variables U such that these three random variables form a Markov chain. We may assume that the range of U is less than or equal than the range of X. Yes, and this is, so those people who are familiar with information theory have seen such expressions many times. So in multi-user information theory, channel capacities, achievable rate regions, and so on are usually given in terms of auxiliary random variables, and it is not different here. And here I just make a short hint to the proof. It's a achievability part, direct part is by standard random selection. We select n1 and n1 times n2 sequences at random from this auxiliary alphabet, where the n1 is given by this, n2 is equal to this. So actually the product n1, n2, the number of all selected sequences, is exponential n times. So this cancel if you take the product, so exponential n times I, U, and X plus minus delta. That is the total number of selected sequences. And it is known that if we select that much sequences more than exponential n times I, U, X, then for every X there will be a sequence among the selected random sequences which is jointly typical with X. There will be actually exponentially many. So we denote by Kx one of the sequences X which are jointly typical with, for every X we consider Kx one of the selected sequences which is jointly typical, and then we select f of x as the I index of these. And then this Kx will be epsilon recoverable for Bob, who knows Yn and the Fxn. So this is a rather standard technique in information theory. And the converse part requires manipulations with information quantities, which is again more or less familiar from information theory. It is necessary to use a key identity from this paper, and so the proof of this theorem is not too hard. And it is interesting to bound the size of this auxiliary random variable. That is also something which is very common in multi-user information theory. One uses the so-called support lemma, which is a consequence of the Karaterodori-Fenchel theorem from convexity. theory of convexity. Okay. So here I would like to make a comment about this concept, how the whole business of common randomness started, at least in information theory. So the first approach to this problem was by Gach and Körner in 1973. They considered the so-called common information of X and Y, which is in effect common randomness capacity in the source model when no communication is allowed. So remember, in the model I considered Alice and Bob observed these two component sources, and Alice was allowed to transmit a certain number of bits to Bob. So if she is not allowed to transmit anything, what can be done? Whether it is possible to achieve common randomness between Alice and Bob if no communication is allowed. And actually I asked this question in the early 70s, and the two people who were young at the time, I myself was a little younger than now, so anyhow they were able to give an answer which was surprising for me, at least at the time, which means that this common information is equal to 0 if X and Y have indecomposable joint distribution. So no common randomness can be obtained in this case, even if X and Y are, even if there is strong correlation between X and Y, if there is no deterministic correlation, so if there is no common function of X and Y. And at least this is not possible to generate common randomness at a rate, at a positive rate. And later results strengthened this result, impossibility to generate any non-trivial common randomness, not even with a positive rate, but even with any fixed amount of common randomness. One cannot do that if unless the deterministic correlation is available. And the strongest result of this kind is due again, one player was Rudy and the other was Peter Gach in 1976 in a very nice paper about the hypercontractivity of the Markov operator. Anyhow, so let me recall that if communication of rate greater than the conditional entropy is allowed, then the common randomness capacity, at least R, the transmission rate, which is achievable by transmitting NR random bits anyhow, so this common randomness capacity exceeds this trivial R by the mutual information. And it means that X and Y have no common information, but the mutual information may be interpreted as a latent common information, which is fully recoverable by communication of large enough rate. So my original idea was I conjectured that this common information should be equal to the mutual information, which was shown to be false. But mutual information is still a common information in some other sense. It is a latent common information. If we are allowed communication at a large enough rate, then the achievable common randomness capacity exceeds the trivial R by the mutual information. So it is a latent common information. Anyhow. Okay, so let me just mention source models with two-way communication. Here Alice sends Bob an R1 bit message, and then Bob sends an NR2 bit message, return message. Also in this case, the common randomness capacity can be determined. It requires two auxiliary random variables. I do not go into the details. Again, some Markov conditions are required, range constraints are given. So the proof of this theorem is more tedious than of the previous theorem, but requires basically the same techniques. But it is open whether this can be extended to the case of several rounds of communication. So it may be that Alice sends Bob a message, then Bob sends a return message, then Alice sends another message, Bob sends another message, and they may repeat. So it is not known at this time whether this theorem can be extended to that case. Now, some comments on the formal definition of the common randomness capacity. So by the definition which we have in mind, the common randomness capacity is the supremum of numbers R, such that for each positive epsilon sufficient large block length n, Alice and Bob can generate epsilon UCR k with 1 over n log k greater than or equal to R. A weaker definition is also possible when the common randomness is not required to be nearly uniform. Only epsilon common randomness k such that the 1 over n times k is greater than or equal to R. And it can be shown via the expector lemma that this weaker definition leads to the same value of common randomness capacity, at least for a large class of models. Or one can use a stronger definition where this epsilon CR, is not fixed, but it has to go exponentially fast as n goes to infinity. This still leads to the same capacity values. And I would like to mention some more recent results. So this research area is not completed yet. There were further results. More recent results on common randomness capacity include paper of Venkatesh and Anantaram in 2000, where common randomness capacity is determined for networks of channels. Okay, so so this is the basic things about common randomness and common randomness capacity. Here I would like to discuss briefly one application, the identification. Yesterday you have already heard about identification by one of the people who developed this concept. So let us say for two-party model, like a channel or source model before, Alice, suppose there is a set J of objects which are considered as the objects which have to be identified, and Alice is given one element of this set J, and she can choose her action depending on the known value of J. And then, of course, the knowledge of Bob, which is represented by a random variable with distribution P sub j, this depends on the j. So denote by Pj the distribution that governs Bob's knowledge. It may be the channel output distribution in the case of channel model, or the joint distribution of yn and the message sent by Alice in the case of source model. Okay, so then we say that the set J is epsilon identifiable for Bob if he can guess epsilon reliably for any I of his choice whether J, the true J object J given to Alice, is equal to I or not. Formally, this means that for suitable subsets di of the range of the random variable representing Bob's knowledge, it is true that if J is the true object, then Pj dj is greater than 1 minus epsilon, but Pj di is less than epsilon if j is not equal to I. So as we had heard already yesterday, it may be that there are many possible events, and the receiver is interested only on whether one particular event occurred or not. So he is not interested in learning exactly what has happened, only whether the event of his interest happened or not. And this identification concept is a model for that case. Now, this set di, if this set di were disjoint, then it would be possible to guess what j was the true one. But these are not, in general, they are not disjoint, they may intersect, so the identifiability does not imply recoverability. So this concept is due to Ahlswede and Duke for the channel model, and remarkably, as we already saw yesterday, the maximum size of identifiable sets grows doubly exponentially with the block length n. So that was a very surprising discovery at that time. Now it looks trivial, but it is the same with every great discovery. Even Shannon's noisy channel coding theorem was a very, very big achievement at that time, and now it looks completely trivial. And this will be probably true with the hard theorems which we have now. After for our grandsons, they will be trivial again. Anyhow, so the identification capacity of a two-party model denoted by C sub id the supremum of numbers R, such that for each epsilon sufficiently large block length n, there exist epsilon identifiable sets, such that not 1 over n times the log j, but 1 over n times the log j exceeds R. Yes? And then Ahlswede Duke showed for channel models that this identification capacity is equal to the common randomness capacity, which we have already seen in the non-feedback case. This is equal to the regular Shannon capacity for transmission. In the case of channels with feedback, it is equal to the maximum output entropy. And remarkably, the proof of inequality works not only for channel models, but for any two-party models that admit real-life transmission at some arbitrarily small positive rate. And here is just sketch the proof idea. The largest part of the transmission length, of the block length, is used for generating UCR. So we have a block length n available, choose 1 minus delta times n block lengths to generate uniform common randomness with this rate. Okay, so this can be generated 1 over n times log k can be larger than 1 minus 2 delta, the common randomness capacity. 2 delta comes because the length is not delta, not n, but 1 minus n delta. Okay, so then after the common randomness, uniform common randomness is there, then use the remaining small block length delta n for reliably transmission a function fj of k, where j is the object given to Alice, and these are suitable functions. Fj are functions which are functions of this kind. This is something which is standard in computer science called hashing. So actually we want to identify this object through these hash functions, fj. So it can be shown by simple computation that if log j is equal to some alpha times log k with alpha less than 1, then randomly selected mapping fj are good hash functions, and it will hold with probability close to 1 that the set j is epsilon identifiable. Now, as I mentioned, Ahlswede proved for the channel model that the common randomness capacity, identification common randomness capacity are equal. To my knowledge, it is not known whether it is true in general. So, for example, for the source model, which I have given before, to my knowledge, it's unknown whether the the identification capacity indeed equals the common randomness capacity. Very likely it equals, but to my knowledge, it's not proven. Okay, so now the remaining time I would like to spend on the cryptography situations. So, as I mentioned, common randomness has many important applications, but arguably the most important ones is for cryptography, where a secret key is needed for encrypting information. And what is a secret key? Secret key for 2 or more parties is simply a common randomness for these parties, which is nearly uniformly distributed, and concealed from an adversary. So it is nearly independent of an eavesdropper's knowledge. So to formulate this criterion, I mentioned this compact formulation, this which appeared in this paper of Csiszár and Narayan. We use this concept of security index. So K is a random variable, and T represents the knowledge of an adversary. So the security index of K with respect to T is equal to, this is log K minus HT plus the, something is wrong here, that should be not HT but HK, I am sorry. So this log K minus HK, that is, the first term is the difference from the uniformity, how much the entropy of K is less than the maximum value, plus the mutual information, which can be represented in this form. So if this is small, if this is less than or equal to epsilon, then the random variables, yes, okay, T represents eavesdropper knowledge. So if this is small, then the K is nearly uniformly distributed, and it gives away very little information about the eavesdropper. So why is it a useful concept? This goes back to Shannon. So if we have such a epsilon secret K, what is an epsilon secret K? An epsilon secret key is a random variable taking values in this set. It can be used for secure encryption of a message M. So M can be any message which is independent of K, of the key, and of the eavesdropper's knowledge. So, and this message takes values in K, in the same set where the key. So then Alice can encrypt M by adding K. We add to the message the key, modulo K. And then transmit this M plus K over a public channel. So then the adversary will learn M plus K, but it does not help her. So the M, from M plus K, Bob will be able to recover not only epsilon recoverable, but fully recoverable. He simply subtracts K, which he knows. And Bob, what will Bob know? Bob, the eavesdropper, okay, Bob learns M, and the eavesdropper remains ignorant about M. Here is a small calculation which shows that the mutual information, so the eavesdropper original knowledge was T, now she knows also M plus K, so her knowledge is M plus K and T, but still the mutual information with respect to M can be represented in this form, and after a small calculation we get that this mutual information is bounded above by the security index. So if the security index is small, then this transmission scheme is very safe. If epsilon is equal to 0, then it is absolutely safe, and this is called in cryptography the one-time pad or Vernam cipher. Okay. Unfortunately, this one-time pad, although absolutely secure, is not very useful in practice because it requires a lot of keys. So every message has to be encrypted by a new key, otherwise the security goes away. So this is how the Americans was able, for example, to catch this, what was the name? This atomic spice. I forgot the name. Rosenberg couple. Anyhow, the Russians somehow made some mistake with the one-time pad and used the same key more than once. Anyhow, so here is the implications of the extractor lemma for this case. So suppose we have two random variables UV which take values with finite sets, and with probability 1 minus eta star, the values satisfy this condition. So the conditional probabilities are bounded above, and eta and alpha are some small numbers. Then for a randomly selected mapping kappa, it is true that the security index of kappa u given v is bounded by this expression. So again, if these alpha, eta are small, then the security index will be small. If they are exponentially small, security index will be exponentially small with large probability. And some corollary, suppose we have IID repetitions of a pair of random variables x and z, and suppose that to any delta there exists some psi such that if k is less than this expression, then this is the statement, that's not suppose, this is the statement. There exists such that the randomly selected mapping will have exponentially small security index and this holds except with doubly exponentially small probability. And the same if we have some additional random variable about which we know a bound on the number of possible values. So anyhow, this lemma, extractor lemma, the great importance of the extractor lemma is that it admits us to produce keys which are safe, which are secure. So if we have we can achieve not only common randomness but secure common randomness. Okay, so let me say something about secret key capacity. Models, let us consider this source model first. Again, this may look, in the case of common randomness, of course, it is not surprising that public communication admits larger common randomness, of course. But it is by no means obvious that public communication admits to generate larger amount of secret common randomness because the enemy sees this public communication. So it was the discovery of Bennett, Brassard, Robert in 1988 and then Maurer in 1993. Public communication can help to generate secret key. And in models admitting public communication, this communication, of course, is fully known to Eve. Eve is the acronym for the eavesdropper. So what is the secret key capacity? Secret key capacity is supremum of numbers R such that for each epsilon sufficient large n, models admit to generate epsilon secret key of rate R such that these two conditions are satisfied. Again, T represents the total knowledge of Eve. Remember, this T always contains the communication, the public communication of Alice and Bob. Here again a comment. Early works required only 1 over n times this sk over t less than epsilon. And Maurer argued that this 1 over n should be introduced because otherwise these models are not good enough for cryptographic purposes. But it turned out that for large class of models, weaker and stronger definitions give the same result, even if we require epsilon not constant but going to 0 exponentially fast, the capacities are still the same, at least for a very large class of models. So here is source models of generating secret key. In first model, Alice may, so again we have these two sources, x, y, but now we have a third source which is seen by the eavesdropper Eve. So actually we have repetitions of 3 correlated random variables. Alice sees x, Bob sees y, Eve sees z. And then what strategies can Alice follow? She may generate a random variable which is independent of everything and send these to Bob. She sends Bob a message f, which is a function of what she knows, over a noiseless public channel. The eavesdropper, of course, learns this f. In the second model, the same, but f can have at most x and r1 possible values. So we have a rate constraint on the transmission. In the third model, any number of communication is possible, so the two persons can generate interactively, perhaps in several rounds. Now, first result about this is that the common randomness, the secret key capacity in the case of model 3, when unlimited public communication is allowed, is lower bounded by this difference of mutual informations, upper bounded by the conditional mutual information. And these two bounds coincide if x, y, and z is a Markov chain. So at least for some cases, the secret key capacity is known exactly. Now this, yes. And the lower bound is achievable already in model 1, when only Alice can transmit. Now here is a theorem which is a stronger result. Again we have model 1 or 2, so only Alice can transmit a message, either without rate constraint or with rate constraint. And then the secret key capacity again is given by such a maximum. Again, two auxiliary random variables are involved. There are conditions, Markov chain conditions on this, and rate conditions. And this is the value of the secret key capacity. In the case of model 1, there is no rate constraint, so this constraint is not there. In the second model, this constraint is here, and the second result is due to Narayan and myself in 2000. The first one was in the original paper with Ahlswede. So just a remark that if in this model we set u constant and v equal to x, then this expression in the theorem becomes equal to the difference of the conditional entropy of x given z, conditional entropy of y given z. And this is achievable easily, direct consequence of the previous corollary of the secrecy lemma. We had this corollary of the secrecy lemma. In this case, for R, we take the conditional entropy of x given y. Yes, because by the Stepien-Wolf theorem, by transmitting at rate x given y, Alice can make sure that Bob learns exactly the hx. And then we are in the situation that this auxiliary function fn has this rate r equal to entropy of x given y. Okay, so this model is easily settled, and this remark can be used also to prove the general theorem. For model 2, however, it is not so easy, so that requires more work. And I would like to mention for model 3, where unlimited public communication is permitted, the previous lower and upper bounds have been improved, but a general formula is still not known. Now, about channel models, I think I started later, so just I would go very fast over this. I do not go about channel models. The channel models were available already earlier. This so-called wiretap channel was available earlier. I am not going to discuss the wiretap channel. I just would like to mention a little bit the multi-terminal source models. So in the multi-terminal source models, we have not one, not two persons, but m persons. I suppose for simplicity that the eavesdropper has no private knowledge. So everything, these are the random variables, repetitions are known to the parties. There is a subset of the all parties denoted by A, and common randomness, secret common randomness, has to be generated for these parties. So the common randomness for this model has been determined in this paper, and I believe in the next talk we will hear more about this. Important point is that here the common randomness, the non-secret common randomness, does play an essential role. Here is the so-called omniscience. Omniscience means that the parties, the involved parties, learn everything, so the totality of all random variables. So we say that a communication is a communication for epsilon omniscience if the communication admits each party in A to reproduce the whole XM. And the omniscience rate is the infimum of such number. So this omniscience rate, the minimum rate of communication which is necessary to make every member of the required set omniscient, plays an important role. So here is a theorem which says that the secret key capacity is equal to the entropy of the total entropy minus the omniscience rate. And this omniscience rate can be given a singleton characterization. Where is it? Yes, here is the singleton characterization. So this is equal to the minimum of such sum subject to certain constraints. These are so-called Slepian-Wolf constraints. Okay, so what else? Multi-terminal channel model, I am not going to this. I think it is time to, even though I started a little later, I hope the next speaker, I am sure the next speaker also needs time, so I stop at this point. Well, thank you for attention.